The Imperial Japanese Navy battleship Nagato survived the kinetic fury of a nuclear airburst as a structurally sound but worn-out target, only to be fatally compromised weeks later by a fundamentally different mechanism of destruction. The former 32,720-ton standard displacement dreadnought remained upright after the second blast, but entered a slow, progressive flooding sequence that ended beneath Bikini Lagoon. By the summer of 1946, the vessel stood as a singular engineering artifact. She was the only Japanese battleship to survive the Second World War entirely afloat. Rather than being scrapped, the massive dreadnought was surrendered and repositioned to the Marshall Islands. She was designated as one of the principal target vessels in a highly controlled series of nuclear weapons tests. The objective was to measure the terminal effects of atomic blasts on heavily armored fleet units. The first phase of the operation subjected the warship to an atmospheric airburst. The detonation occurred roughly 1,640 yards from the vessel. The atmospheric overpressure and extreme thermal radiation swept across the ship, stripping exterior paint and warping exposed topside fittings. However, the fundamental structural integrity of the warship remained intact. Following the blast, engineering teams boarded the vessel to assess the damage. As a limited test, a skeleton crew operated one of her boilers for 36 hours without reported trouble. That result showed that some machinery could still be made to function, but it did not prove that the full steam propulsion plant was combat-ready. The engineering parameters shifted entirely for the second phase. The next atomic device was suspended below the surface at a depth of 90 feet. The warship was moored approximately 950 yards from the exact point of detonation. This configuration changed the physical nature of the attack. When the underwater device detonated, it did not expend its energy into thin atmospheric gases. Water is far less compressible than air, so the blast coupled far more efficiently into the surrounding water mass, creating a short, high-velocity pressure wave. This dense wall of force propagated outward through the lagoon with devastating mechanical efficiency. The hydraulic shockwave struck the broadside profile of the battleship. Dreadnought armor geometry is specifically engineered to defeat incoming naval artillery shells and aerial bombs. The thickest steel plates are concentrated along the waterline and across the primary armored deck. The plating located deep along the lower hull and the lowest bilge sections is comparatively thin. The dense hydraulic hammer effect focused massive energy against these vulnerable lower hull areas. The force of the underwater wave dented and ruptured shell plating, opened major leakage points, and permanently compromised the watertight integrity of the lower compartments. The ocean surface above the detonation immediately erupted into a towering hollow column of water. A massive base surge of displaced water and heavy mist then washed over the target fleet. When the turbulence settled, the warship was still floating, battered above the waterline, upright in the target array, and outwardly capable of being mistaken for a survivor. Below the waterline, the damage moved from impact to consequence. Flooding spread through deep structural voids in a ship whose internal watertight integrity had already been judged poor, and existing weaknesses in subdivision allowed water to pass beyond the first damaged spaces. The ship was not sinking at a rapid rate, but the flooding was progressive, unrelenting, and no longer controllable. Thousands of tons of reserve buoyancy fought against the incoming ocean. A slow and heavy starboard list began to develop as the starboard compartments filled with water. One full day passed without a catastrophic plunge, then another. The gradual settling process remained entirely mechanical, as the water level overtook one compromised space after another. By the fourth day, the delay itself had become the measurable consequence. The battleship's massive internal volume slowed the final loss of buoyancy, even as the below waterline damage made the outcome irreversible. Roughly 4.5 days passed between the Baker detonation and the final sinking of the massive dreadnought. During that prolonged time window, salvage personnel and repair resources remained in the surrounding lagoon, but their priorities were shaped by radiation control rather than ordinary damage control. Under normal operational conditions, a slow starboard list would trigger a major damage control response. Naval engineers possessed the pumps, patch materials, and technical expertise required to stabilize many flooded ships. Yet Nagato was apparently never reboarded after Baker. The barrier preventing human intervention was invisible, immediate, and thoroughly dangerous. The massive hydraulic force of the blast excavated the lagoon floor, mixing pulverized sediment with heavily irradiated seawater. This toxic slurry was hurled outward in a sweeping base surge that entirely engulfed the listing battleship. As the heavy mist finally cleared from the sky, it left behind a highly concentrated sheen of radiation across every horizontal surface. The armored decks, the mooring cleats, and the massive anchor chains were thoroughly coated in this invisible hazard. The ship still looked recoverable above the waterline, but radiological surveys and standoff observations showed that sustained work on the contaminated hull was impossible in the available time. Heavy pumps and secure watertight boundaries would require prolonged manual labor deep inside the damaged ship. Heroism in this context demanded disciplined restraint. The institutional decision was made to enforce a strict quarantine zone. The battleship was entirely abandoned to the slow and methodical physics of internal water displacement. From that point, monitoring shifted to standoff observation. Sometime during the dark hours of a late July night, entirely unseen by the massive observation fleet, the final margin of reserve buoyancy collapsed. The massive structure finally slipped beneath the surface, removing one contaminated target from the open air while leaving the broader lagoon contamination problem unresolved. Decades passed, and the extreme radiological boundary around controlled wreck diving gradually faded. Many short-lived isotopes naturally decayed over time, and organized dives are now treated as low radiation exposure when artifacts are not disturbed. But Bikini Lagoon has not returned to a pristine baseline. Bottom sediments still hold persistent fallout contamination, and the wreck's depth imposes the modern access barrier. The main wreckage rests on the lagoon sediment at roughly 165 to 170 feet, where ordinary air diving pushes beyond normal recreational limits and introduces serious narcosis, gas density, and decompression hazards. Even a brief observation period at the bottom can require meticulous staged decompression during the slow ascent to the surface. On the morning after the late July night, observers faced a blunt absence on the surface of the lagoon. The battleship had vanished from the target array. Nagato had capsized and sunk unseen during the dark hours. Later inspections and surveys, including diver observations, documented the inverted wreck on the lagoon floor at roughly 165 to 170 feet. Those observations established location and orientation, but not a complete condition record of the hull. For decades, the specific physical state of the wreckage remained an enduring historical mystery. Finding the exact geographical coordinates of the sunken vessel was merely the first operational hurdle for modern survey teams. Accessing the site requires navigating a rigid legal and ethical boundary within the sovereign territory of the Republic of the Marshall Islands, inside a World Heritage landscape protected through local law, traditional authority, permits, and international heritage recognition. That framework creates the operating ceiling for any modern survey. Under that ceiling, no intrusive structural sampling is permitted, no cutting equipment may be used on bulkheads, and no artifacts or structural fragments may be recovered for surface analysis. Wreck penetration, where an operator allows it, remains limited to trained technical divers with overhead environment experience and strict safety controls. For documentary survey work, the safest scientific objective remains external observation and non-contact mapping. The operation demands absolute discipline. Teams must extract high-quality forensic data while leaving zero physical trace of their presence on the hull. To execute this strict survey objective, many modern exploration teams favor advanced closed-circuit mixed gas technical diving methodologies. Traditional open-circuit equipment is possible only under strict technical planning and operator logistics. For repeated complex surveys at this depth, closed-circuit systems are often far more efficient. Specialized divers therefore wear complex life support systems that chemically scrub exhaled carbon dioxide while maintaining a controlled oxygen partial pressure in a closed breathing loop. To safely operate at the bottom, the internal breathing loop is diluted with a helium-based gas mixture chosen for the depth. This technical breathing gas greatly reduces nitrogen narcosis and improves working clarity in the high-pressure environment. The advanced mixture helps human operators retain the judgment and steady physical control required to execute precise measurements in a deeply hostile zone. Furthermore, closed-circuit systems release very few routine exhaust bubbles, reducing the chance that delicate, corroded structures overhead will be disturbed by turbulent gas streams. Deploying this specific method, highly specialized survey teams descend through the dark water column to visually document the site. They carry high-intensity lighting arrays and advanced digital camera sensors, systematically swimming along the exact perimeter of the steel mountain. Multiple sequential dives are required to cover the immense physical distance of the hull. Using that disciplined approach, the teams establish a detailed visual map without touching the wreck. They confirm where the primary hull mass rests relative to the surrounding seabed topography and plot the exterior boundaries of the primary site. The non-contact method satisfies the heritage restrictions, but arrival at the bottom immediately complicates the forensic task. Illumination reveals not a straightforward battleship profile, but a disorienting structural geometry. When a massive armored battleship rolls over and comes to rest inverted, it creates a formidable geometric trap. The dreadnought inverted during the sinking process, pinning many of its critical upper surfaces against the unforgiving lagoon sediment. This resting orientation governs every single observation made by modern teams. As survey personnel descend through the upper water column, they do not encounter the classic silhouette of a military vessel. There are no towering masts or raised forecastles. Instead, the first physical structure materializing in the dim light is the vast, flat expanse of the lower hull. The absolute shallowest structural features of the entire wreck are the 4 giant bronze propellers. These massive propulsion blades point directly up toward the surface, sitting exactly 108 feet below the ocean waves. That shallow propulsion position confirms both the capsize and the continuity of the primary hull block, turning the lower hull into a steel ceiling over the seabed. Moving deeper along the sheer vertical hull walls, the survey teams encounter a profound gravitational anomaly. Battleship main gun turrets are incredibly dense steel structures designed to rotate inside heavily engineered circular barbettes. In many capital ships, these immense weapons depended heavily on their own weight, seating arrangements, and retaining structures to remain in place. Consequently, when a heavy warship rolls over during a sinking event, turret movement or separation is a serious possibility rather than a certainty. Yet, as survey divers work near the deeper portions of the inverted hull, they visually verify an extraordinary mechanical deviation. The massive 16-inch main guns remain in their mounts, with the turret structures still seated in their barbettes despite the capsize. The guns project from the inverted hull, while the tops of the turrets rest against or near the bottom. Documenting this rare retention provides a significant knowledge gain for the expedition, suggesting that the turret seating and surrounding structure retain the batteries through the underwater shock, the capsize, and the subsequent bottom impact. The same inverted geometry that preserves the main batteries also limits what the survey can prove. The 1946 target arrays were designed to measure nuclear yield effects against exposed topside architecture, especially the armored deck and immediate upper superstructure. With the hull resting upside down, much of that evidence is pinned against sediment or crushed into the wreckage mass. Modern visual surveys can still record displaced superstructure and exposed features, but they cannot comprehensively evaluate upper deck warping or the primary atmospheric bomb damage. Even with that limitation, perimeter mapping establishes a physical baseline, a continuous main hull large enough to anchor the rest of the site. However, slowly navigating the long perimeter of this continuous structure reveals a dramatic structural displacement. The pagoda mast, bridge levels, and upper command architecture lie crushed and displaced beside the inverted hull rather than rising from it. The condition of these massive components indicates that violent shearing and crushing forces acted across the superstructure, directing the external survey effort away from the main hull and outward into the dark perimeter. Severing the primary command tower from a heavily armored dreadnought requires an immense application of kinetic energy, and the position of that separated debris becomes a timing clue. Moving outward from the primary wreckage, survey personnel use the surrounding sediment and debris placement to read the final dynamic sequence of the sinking event. At this stage, the forensic task is limited to interpreting the scattered remnants through observation alone. Scanning the dark lagoon floor just off the port side of the wreck, the teams discover a massive, isolated debris zone. The iconic pagoda mast lies completely detached, resting laterally across the ocean floor. This towering steel structure once served as the primary command and control center for the warship, consisting of a dense lattice of heavy observation decks, armored rangefinders, and thick steel platforms. Finding this enormous component separated from the primary wreckage block provides a crucial piece of site formation evidence. The physical condition of the fallen mast is heavily damaged, severely crushed by extreme mechanical stress, but it remains a single recognizable structural entity rather than a pile of vaporized fragments. Because the mast lies adjacent to the port side and remains recognizable, it helps reconstruct the sequence of separation. The heavy structure did not simply vanish during the atmospheric airburst, and the surviving wreck pattern is consistent with major displacement during the final sinking and bottom impact rather than complete destruction at the surface. Instead, the massive steel tower lies immediately adjacent to the port side. That proximity strongly suggests that much of the pagoda structure remained with the vessel through the slow flooding period and descent, then broke away or folded as the inverted hull and superstructure met the dense lagoon floor. Beyond the highly localized footprint of the crushed mast, the survey teams must evaluate the wider scatter geometry of the surrounding area. When a heavily damaged warship sinks through deep water, extreme hydrostatic pressure often compromises the weakened internal bulkheads, causing a violent mid-water breakup. This type of catastrophic structural failure tears the hull apart, distributing thousands of smaller internal components, heavy piping, and loose secondary armaments across a vast, chaotic debris field. To evaluate this possibility, teams execute long perimeter sweeps, projecting high-intensity lighting far into the dark water to locate off-hull scatter. Surveying the outward perimeter of this specific site reveals a telling absence. No large, chaotic debris field has been documented around the main hull. The sediment surrounding the vessel is not dominated by shattered internal machinery or loose structural fragments. The limited scatter supports a cautious conclusion. The dreadnought does not appear to have suffered a catastrophic mid-water breakup before bottom impact. That intact descent imposes a hard forensic limit. Because the hull did not shatter and spill its internal contents across the seafloor, no loose interior debris is available for external evaluation of metallurgical yielding from the 1946 blast. Yet, while the exterior footprint remains definitively stable on the ocean floor, the deep internal architecture is not frozen in time. The immense, continuous mass of the vessel is quietly and progressively failing. Inside the dark recesses of the deeply submerged stern section, a decades-long record of mechanical fatigue is written into the steel. The warship appears to rest quietly upon the lagoon sediment, but the aft structure is visibly broken and collapsed. Modern observations show major damage concentrated in the stern, where shell plating is ripped, separated, and weakened by long exposure in seawater. The immense steel plating and internal framing in this region have yielded to a combination of original damage, bottom impact, pressure, and marine corrosion. This localized deterioration is consistent with the stern weakened by Baker damage, bottom impact, corrosion, and the stresses of resting inverted for decades. The underwater shock of 1946 damaged the hull below the waterline, but the modern stern failure marks accumulated weakness rather than a clean map of the original hydraulic blow. However, this active mechanical failure imposes a harsh temporal limit on the long-term forensic record. As the aft section progressively caves in on itself, the heavy steel bulkheads shear and distort far beyond their 1946 configuration. The collapsing mass actively destroys the original bomb damage, twisting the broken plates into an unrecognizable tangle of heavy steel. This ongoing destruction creates the proof ceiling. The precise configuration of the ultimate structural failure is being erased by the collapse itself. There is no safe engineering method to reverse the collapse, and the exact physical point of the fatal breach is permanently lost within the crushing weight of the failing stern. The accelerating danger of the collapsing stern directly dictates the modern administrative reality of the site. Access to the historic wreckage is conditionally permitted. Specialized technical operators may descend for external visual surveys, but strict jurisdictional authority prioritizes human safety and long-term historic preservation above aggressive underwater exploration. The managing authorities demand absolute compliance with a heavily restricted non-contact methodology. Physical contact with fragile steel and unsafe interiors is avoided, and hazardous voids filled with sharp, unstable structure are treated with extreme caution. Where wreck penetration is allowed at all, it belongs only to trained technical divers under operator rules and overhead environment safety limits. Furthermore, the removal of any historical material is strictly prohibited. The modern survey objective is fundamentally divorced from traditional naval salvage. There is no operational effort to stabilize the hull, patch the failing seams, or arrest the degradation. When access is granted, permitted divers and survey teams document the wreck's condition without removing material or altering the site. She remains locked in deep water, an untouched casualty of the atomic age, slowly yielding to the finality of the marine environment.